All right, everyone. So welcome to the stream. This is our first camp for FTC programming. My name is Ritesh. So who are we? STEMpump is a student-led initiative that teaches students the best of STEM technologies for free. We cover everything from programming to robotics, even game design. Due to the current pandemic, we decided to take all of our in-person classes and create them into an online platform known as STEMpump Online. We are based out of Dallas, Texas, so hopefully some of you guys from our in-person classes are on the stream today. So how does this camp work? So FTC Programming Art, this camp goes for 3 weeks. We're going to meet every Tuesday from 3 to 5 p.m. So the dates are May 26th, June 2nd, June 9th, and all of them from 3 to 5 p.m. During the stream, feel free to ask questions in the chat. We're going to have designated periods where we're just going to be answering questions. And after the stream, after 5 p.m., if you have any more questions, feel free to reach out to us on Instagram, Twitter, Twitch, Discord, any of our social media. The great thing about this course is that if we don't finish anything today, we can pick it up next week, and we'll keep on going from there. So over the next 3 weeks, here are some of the topics we're going to cover. And they're subject to change. We can add some more, we can take some away, but it's really just seeing what you guys want to learn. So most likely today we're going to be going over the basics of Java. We're going to go talking into OpMode design. We're going to talk about TeleOp and autonomous. And then hopefully next we can go into vision, encoders, sensors, GitHub and version control, and something we call a dynamic workflow. And then we can kind of see where we go and play it by the ear. So for those of you that don't know what FTC is, and this is going to be your first season next year into it, FTC is otherwise known as the First Tech Challenge. It's designed for students in grades 7 through 12 to compete head-to-head by designing, building, and programming a robot to compete in an alliance format against other teams. So basically 2v2 robots, competing, trying to score. We're kind of going to talk about that a little bit today. The robot's going to be programmed with Java, but there are other options such as Kotlin and Blocks, which is more of a drag and drop format. Kotlin's for a lot more advanced people that don't want to use Java, but most likely a lot of teams you're going to be seeing are either using Java or Blocks, and more older teams will be using Java. So what is Java? Java is a general purpose programming language that is class-based, object-oriented, and designed to have as few implementation dependencies as possible. You don't really need to understand what this means, as throughout this course, these 3 camps, you're going to really understand, all these different types of things that is mentioned in this definition and how we can apply them to FTC robotics. So what is Java used for, though? Well, for one, it's used in FTC robotics, and it's also used to make web page components, create applications, and servers for major companies. In this camp, we won't go in depth into the language, just scraping the surface for the next few weeks into programming your robot. Your Java skills will grow over the next few weeks, and if you want to explore more into Java, you can sign up for our camp on Java, which is going to be in a few weeks, I think. So let's get started in Java. I'd appreciate it if you go to this link right here, stempump.com/r/Java. And we're just going to go here. So you should see something like this, and this is an online IDE, and we're going to kind of explain what that means in a little bit. So right here, we have public class hello world, and this is what called our class. So this file's name is helloworld.java, and you're going to see this once we start creating our OpModes today, that we're going to take this and manipulate it into a way that we're able to use it. And right here, this is called our main method. So whatever we're going to print on the side will be put inside of this. So right now, all we have is this system.out.println statement. And basically what that does is it prints text to our display. So if we click execute right here, we can wait for this to load up. And you can see right here, it says hello world. So it's as simple as that. And if we just change this, so change it to hello everyone, click execute, and it works perfectly. We want to make sure that we stay within the quotes because I'm going to explain to you what variable types are and how that works throughout Java next. So in FTC, you have a lot of different types of things you can do, but with Java you have a set amount of variable types, and a variable is a value that we could be changed through the code or reset originally. there are really only 5 critical variable types in Java. I mean, there's a lot of them in Java, but only 5 critical in FTC, and that is the integer, the float, the double, the string, and the boolean, and we're going to go through each one. So first, let's start with the int. So the int stands for integer, and it's a variable that holds a numerical value that can be accessed when called upon. It basically holds integers or whole numbers. So to call one of these, we can just write int, and then we can say number equals 1, and then semicolon. In Java, we end every line with a semicolon, as you can see right here. So in this, we declared what type our variable was. So we say it's an int. We say it's going to be called number, and it's equal to 1. So this is one way to write it. Another way to write it is if we wrote int number 1, or let's just do 1 like that, and we end it with a semicolon. So this is an uninitialized variable, meaning that we never gave it a value, right? So then what we can do is we can write number 1 equals 2, or even just number 1 equals 1. And these two things mean the exact same. It's just how you want to write it, because some people might declare it in the top and then maybe initialize it with a value later below. But right now, let's just focus on looking at this. And we can actually see if we replace this hello everyone with the quotes and everything like that, we can actually just write number, hit execute, and it shows up 1. We can change this number, make it 2, and there we go, we got 2. Next, let's talk about what a float is. So a float is similar to a number that has basically a decimal in it. It's meant to be called as a floating point. So this variable has up to 7 digits of precision. So if I just type in, this, and then I type in float point, and I execute it, it gets upset because of how many digits we put in. So let's just delete some, execute, still getting upset. Why is that happening? That's weird. What? Oh, sorry, yeah. Getting my language confused. So right here, we have to declare it with an F versus, what we're going to talk about later is a double. So we can just add, a bunch of digits, and it'll show up. But after a certain point, it rounds them. See, it won't show any of these because it only has up to, 7 digits of precision, as you can see right here. So now let's talk about what a double is. And floats aren't as common in FTC or any language really, because when you have access to the double, you just have more value of precision, and it's also just easier to write. So if I wrote double value, I can write, 12.78 this, whatever. And then I can print it, execute, and we get almost everything except that. So this is what we're going to use a lot today when we're going to talk about, how to do servo positions and calculating our gamepad values into power. We're using the double, so the float is not used as often. So when we first saw our hello world printout, that is called a string. And a string is basically a value that means text. So if I wrote string message equals hello world, did this, and changed that to message, I can hit execute, and right here we have hello world. I can change this, just hello, execute right here. Now if I type in a number right here, it'll print out that number. But the cool thing is I can add, words, letters, and characters after it, and it still treats it as a string. So this won't be as manipulative as changing one of these things, which I can add values to, subtract. And we're actually going to play with that in a little bit. So this is what we have right here. Next, we're going to talk about booleans. So a boolean is basically a true-false value. So we can say, is red red? I'm going to say true. And then right here, we can type is red red. We're going to get true. We can change this to false. So now we can actually let's make a really quick conditional, and we're actually going to explain what this is in a little bit. But we're going to write if, add two parentheses, value equals true. Let's create a Boolean named value, set it to true. And we're going to open it with these curly braces because it shows us what we want to happen if value is equal to true, in which it is. System.out.println, this is true. And this is an example of us using our strings. And then we're going to add else, open this again. So if it's not equal to true, so if it's false, system.out.println, this is false. Run that, just comment this out. So this is a true, or this is true. And then watch if we change the value to false, hit execute, and right here, we get that this is false. So now we're actually going to talk about more into these conditionals. So we start out with this if-else statement. So let's kind of go more in depth into that. So let's create an integer named first number, set it equal to 4, and then get a second number, set it equal to 4 as well. So in the same process as what we did right here, we can actually change this to if, add our parentheses right here, because we want to make sure that our conditions is what they're called, fit inside there. We're going to write if first number is equal to second number, we are going to print out 4 equals 4. So when we set a value to our variables, right here, we're using a single equal sign. And that basically says make first number equal 4, make second number equal 4. Right here, when we're doing our condition, we're using 2 equal signs. So what this means is we're checking if they are equal. We're not setting one to the other. We are making sure that they are equal. So if I run this, get 4 equals 4. If I change any one of these, let's just change that to 5. We don't get anything printed out right here. Another thing we could do is we could just ask if this is equal to 5. Change 5 equals to 5. And execute. And 5 does equal 5. So let's talk about operators though. We already mentioned that double equal signs is used as a comparison operator to compare two values together. So let's create an integer named a and set it to 3. Let's add another integer to b and set it equal to 8. We're going to create a Boolean called outcome and not attach a value to it. We're going to write outcome equals a is less than b. And actually, let's uncomment this out and write outcome. So if I run this, you get true because 3 is less than 8. Now let's try something else. Outcome equals a greater than b. Now we're going to be able to get false because 3 is not greater than 8. We could also do something where we do greater than or less or equal to. So we can do a. So outcome, if it's equal to or less than 4, so it's going to be true. Let's do outcome equals b greater than or equal to 6. And execute. It's going to be true, but if I change that to 2, false. Let's change that up to 8. We are going to check if what we did above, if we're going to double check if they're the same. So we're going to ask, is a equal to b? False, a is not equal to b. 3 is not equal to 8. And then we can do a not equals. So a, and then we're going to do this exclamation mark equals b, semicolon. We're going to click execute. And we get True, because 3 is not equal to 8. Now we can actually talk about ORs and ANDs, where we can evaluate multiple conditions to give us a final answer. So let's do outcome if A is greater than B, and then we're going to add these two lines. These aren't else, these are these vertical lines, which is at the top of one of the slashes on your keyboard. If A is greater than B, or if A is less than B, we're going to get true. Well, why is that? So we only asked if one of these was true, because we used OR. So we checked that A was greater than B. 3 is not greater than 8. That would be false. But since this is true and we're using an OR, then the overall outcome is true. Now let's try if we use an AND. So we'll do the same thing, but instead of 2 lines, we're going to do double ampersands. We're going to do this. Execute. We're going to get false, because this statement is false and this one is true. And then we're going to check. We can also do this. So if we make another Boolean called value result equals true, we can, if I just type that in, outcome equals result. So outcome will equal result. Result is true. So outcome basically equals true. Execute. True. Now if I add this exclamation mark here, we can click execute, and it becomes false because this is called a logical not, and it automatically negates this Boolean value. So now using all these operators to evaluate conditions, we can actually start using our if-else statements to develop some more things like we did up here. So if A equals B, system.out.println, you will get pizza. Hit execute. Nothing comes. Nothing comes at all. So let's add an else statement to this. System.out.println. You will not get any pizza. Execute this. And that's true because, 3 is not equal to 8. I've changed that back to 8. We will get pizza. Another way we can write this is a shorter way, and it's more freehand. So we just do A equals B, system.out.println pizza. We do else println no pizza. Execute. That. You get pizza. A is equal to B. A equals 8. But what if we want to be able to do some more advanced things than this? We can do something called an else statement. So we can do if A is equal to B, else if, and then here we can add another condition. So if A is less than B, just fix some of this indenting. So if A is less than B, let's revert this back to 3. Maybe the person will get half a pizza. You'll get half a pizza because we added this other else if. So it basically says, okay, we're going to see if this is true, and then then decide what we want to do. So 3 is not equal to 8. So this automatically false. We can't do this. But is 3 less than 8? Yes, it is. So then we're going to do this. Now, if we did, 20 right here, then it would default to this last value because it doesn't meet any of these two conditions up here. Okay, so this is kind of sort of the basics of Java that we're going to look at for now, and then as we get into making OpModes, we're going to kind of go more into it. So for right now, I'm just going to check the chat, make sure that you guys have your questions answered. Does anyone have any questions right now? Going too fast? I'll slow down a little bit then. Okay, I think I'm going to go through all the code one more time. Seems like I went a little bit too fast. Sorry about that. So right here are all our variables. So, or before that, let's go even further. So this is our class. It is also the name of this file, which we can't see because we're in this online, coding area. And it's called hello world. Right here is our main method, public static void main string, and then these args. And everything that's shown on this side will be happening inside these two curly braces. So right here is our first variable type that we talked about. It's an integer, so an integer number without any decimals. So we can do 2, we can do 3, 4, -4. As long as it's an integer or a whole number, then we're good. That's what an integer is. If I type in 5.4, it's going to get upset. It says you should be using a double, not an int. So I change that back to 5. What's that? Right here, our next data type we talked about, a float. It is basically the same as adding a decimal value. So if we have this number right here, a lot of decimals, the thing about a float is that we always have to add an f at the end of it, and then we have to go through 7 digits of precision because it can't do any more than that. Otherwise, we'd have to use a double, which is a lot more common. So we type in the word float because we want to say that our float, or this is our value called a float. The name is float point, and it's equal to this. So if I add a system.out.println, and that's right, float point, execute, we get 0.68448484. Now, let's count that. We have 1, 2, 3, 4, 5, 6, 7, or 8. We have 8 right here. We have 8. So we have a lot more than 8 right here, because after those 8 digits of precision, the float just rounds. So then that's why we have the double. With the double, we can make sure that we don't have to round, and we can almost get the exact precision that we want. So if I just change that to double value, execute, you get our entire number right here. We can keep on adding a few more. Still get it. So you can add a few more. Still get it. The double has a lot more precision to it because once you are dealing in super small numbers like this, then it gets really hard for the float to keep up. With the string, this is basically any text or phrase. So we can write, my name is Jeff, or I like strawberries. We basically say we have a string of message. The name is message. It is a string, and it's equal to I like strawberries. We have a bool, and so that's how we write that. It's just a message. We can do this message. It's cute. Right here, we have all of this. So then we're going to talk about booleans, and a boolean is a true false value. It can't be anything else. It's either yes or no, true or false, 1 or 0. It's only 2 values we can really apply to it. We made a boolean called isRedRed, set it to true right here, and I can print that, and it will come up as true. So red, there, it's true. Now, if we have this other boolean we created called value, value is equal to false. We checked if value is equal to true by using the double equal sign operator, which we're going to talk about, which I'm going to review one more time. This is true, this is false. There's only two options, it couldn't be anything else. Well, this is false, because value is not equal to true. Right here, we declared an integer named first number equal to 5. Remember, an integer cannot have any decimal points to it. It is only going to have a whole number, positive or negative. Same with second number. It is an integer. We can't have any, decimals or anything like that. Otherwise, it wouldn't work. It can be a whole number integer. We asked, well, is first number equal to 5? And we did get 5 equals 5, because that is true. We can do, is first number equal to second number? And we don't get anything, because we never, if it's not true, it's nothing else, but we didn't really write anything if it wasn't true. Here are all of our operators that we have. So we created an integer named a equal to 20. Remember, no decimal points. Integer named b equal to 8. Also no decimal points. Created a boolean named outcome. We never gave it a value. So this boolean is just a boolean. It's not true, it's not false, it's in this middle area. But we can't really use it in comparison until we give it a value like we did all right here. We also created another boolean with a named result equal to true. In the first operation that we did right here, comparing a and b, we checked if a was less than b. From here, we can check is a equal to b. So we're gonna actually I'm just gonna paste outcome right here. We're gonna execute, and since 20 is greater than 8, false. Writing this is the same as writing that. See, still false, same thing. Then let's check if a is greater than b. So is 20 greater than 8? Well, yeah, it is. True. Now let's see if a is 20 less than or equal to 4. False. But if I made this 4, true. So we're going to change that. 20. We have we're going to take our outcome equals b less than or equal to 6. Well, we have 8. 8 is greater than 6. We can execute. This is true. We can change this number up right here and make that 5, and it becomes false. Now if I made it 6, true. This next operator, which we used before above right here and here, is checking if things are equal to each other. We aren't setting values, we are checking if one equals another. So we're checking if a equals b, otherwise known as checking if 20 equals 6, and 20 does not equal 6, so we should be able to get false as our value. From here, if I made this 20 true, 20 equals 20. Now in this next one, if we use the exact same values, we're going to get false. But why is that? Because we have this exclamation mark here, and this is we can also use down here. And basically what this says is a not equal to b. Well, a is equal to b, so false. A is equal to b, so it has to be false because it is not equal to b. If that makes any sense. And then right here we start talking about how we can use multiple conditions to evaluate an expression, basically. So we have a is a greater than b, or, this means or, is a less than b. Well, what we have right here, 20 equals 20, this would break it, because we don't have an option for equal to each other. So if I do 19, I'll just paste that under there so you can actually read it. True. Even if I made this 21, also true, because one of these conditions is true. 21 is greater than 20, but it isn't 21 is not less than 20. But the OR just matters if one of them is correct. This next one, we do AND, which means that both of these have to be correct. So if we run it, we're going to get false. Because while 21 is greater than 20, it is also not less than 20, which means that it must be false. So above here, we created our Boolean of result, and we set it equal to true. Our outcome is going to be equal to the exclamation mark result. And this is called a logical NOT. And basically what this does is it reverses the value of this Boolean. So since this is true and it's going to reverse it, our answer is going to be false. If I change that to false, it'll change it back to true. Right there. So right here we talk about conditionals. And basically what that is just saying if and else statements, if you know what those are. And basically saying if this, then this. So in a real life example with robotics, if I press this button, then what's going to happen? Or if I don't press this button, then what's going to happen? So if I press the button, the arm moves up. If I let go of the button, arm moves down. So in this instance, we said if A is equal to B, you will get pizza. Well, 21 is not equal to 20, so we don't get pizza. However, is 21 less than 20? No, it's still not. So we're actually going to go to the next statement, which is the last case resort. So basically, if this is false, we go to this one. Now, if this is false, we automatically go to this one no matter what. However, if this one is true, then we never even go to these ones. If this one is false, then we go to the next one. If this one is true, we never go to this one because we've already declared what we want. And then here's the shorthand way to write it. You don't need to have these curly braces, but it's good habit just to get into it so you can understand where your code stops and ends. Another cool thing you can do is we can actually do a lot of math-based stuff, and this actually comes in handy when we're doing robotics, when we're going to start talking about controllers and how our buttons are pressed and using triggers and such. So I can write int a equals 7 plus 10. Let's not name it int a, let's just name it int z. Well, 7 plus 10 is 17. So if I do system.out.println, and that's what that means. We're asking our system to output and print the line. Shorthand way of getting text up here. We can write, we can just type in z, hit the word execute, and we get 17. Let's make another one. Let's do int, let's use a double right now. Double 2.5, or double y equals 2.5 times 6. We can write 6. So our answer, if it loads, 15.0. Well, why is the 0 happening? Well, this is a double, and Java wants to tell you that it's a double, not an integer. If we remove the decimal point, then you would think that, oh, it's turned into an integer, but really it's still a double. I can change this to float, add some f's at the end to indicate that they're a float, not a double. Same thing, same answer comes. So we addition, multiplication. We can also do subtraction. So let's do 50 minus 20. Let's do F, execute. We get 30. Now let's do 20 minus 30, or 20 minus 40. Execute, negative 20. Because integers, they can all have negative values. Except this one, the integer can't have any decimal points, this isn't as precise, and the double's the better way to go. We can also do some cool things with our strings. Or honestly, let's do division first. So we can actually just do int r equals 10/2, and our answer should be 5. It's 10 over 2 and 5. So then we can do something called concatenation. So we just write this message is, and let's just write that much. Then we can add a plus sign right here, and we're going to write very short. Execute. This message is very short. Now, why would we want to do that? We could just write this, and we get the exact same answer. So here's the reason why. If I want to write this, you can write 7 added to 10 equals, and rather than figuring out how that works, you can just write plus z. So you already did the math right here. We do execute. 7 added to 10 equals 17. Now we can take this one step further. We can just do this. We can create int first num equals 8, int second num equals 9. So we can actually just remove that. We can write first num plus added to second num plus, we always have to be adding this, so we have our string right here adding to these numbers equals, and we can write int answer equals first num plus second num plus answer. Execute. 8 plus 9 equals 17. The cool part about this is I can change this value to say that large number, and auto updates right here. Another way we could have wrote this is by basically just copying and pasting this line, moving that first, and we can actually add parentheses right here and actually do first num plus second num. Same answer, because we really just put the values right here. Now removing these parentheses, what happens? We get a completely different number right here. And if you see, this is second num, this is first num. Because what it did is it concatenated it. It didn't add the numbers together, it added it to the string, which is why these parentheses are so helpful. So Java follows PEMDAS, if that's something you've studied in school, where it basically talks about, parentheses, exponents, multiplication, division, addition, subtraction. It follows the exact same thing. So if I do int math equals parentheses 5 times 8 divided by 2 plus 17 minus 6, it would approach it the exact same way as your calculator would, or anywhere else you're calculating with PEMDAS. Oh, I forgot to print it. And we get 31. And that matches to how we would have actually gone for it. So you do 8 divided by 2, you get 4, 4 times 5, 20, and then 17 minus 6, 11, 20 plus 11, 31. Okay, so I'm going to go back and check the chat really quickly to make sure that you guys are doing good. So you're just having issues with latency. Right now. Okay, so I think we're going to continue after that. If you guys have any more questions, feel free to ask in the chat. So we're just going to keep on going. So right now, we're actually going to talk about the FTC control system. And how that works is the FTC control system is a method of communicating with a robot. So to communicate with your robot, FTC has a system called the point-to-point control system. And how it works is you have Android devices and a Wi-Fi direct connection, and you can operate your robot wirelessly. We're going to kind of talk about that a little bit in a little bit. So in an FTC match, there are two phases, an autonomous phase and a driver-controlled, otherwise known as tele-op or tele-operated phase. In the autonomous phase, the robot operates and completes tasks without any driver input or controls. It can only rely on sensor data and the program. In the tele-op phase, there are one or two drivers that control the robot, giving it input to perform operations. So here are kind of the main differences between the two. We have tele-op, which is basically otherwise known as driver control, and is 2 minutes and 30 seconds long. The goal is to complete the main objective. We're going to kind of talk about what the main objective was for the last season, which was Skystone. And in the last 30 seconds of tele-op, it's called endgame, and there's a lot more objectives that pop up. In autonomous, there's no driver control, so there's no input that the drivers could possibly give to the robot. It all has to do everything on its own. It is 30 seconds long. The robot moves with 100% code with no inputs from any players, only what it has, and usually for the past few years, there's always been a form of vision involved with it. So let's look at last season's Skystone game. So in autonomous, there were goals to use vision and or sensors to collect Skystones. So if you can see, we have these 6 stones right here, 6 stones right here, and these ones with the little black fronts are called Skystones, and they had little pictures of what was assumed to be the Millennium Falcon's interior on them. Your robot could start, anywhere on this wall. And so our robot kind of started right here, and it would scan the 3 stones and figure out where the Skystone is, place it, come back, grab the other one. So that was one of the first goals. Another objective was to park on this tape, because that also gave you points. Another objective was to grab this thing called a foundation and to bring it into this corner where it'd be touching. Some teams, if they had time, would take stones from here and then drop them onto there and score the extra points, or just get points from bringing stones across the bridge. In tele-op, the main objective was to take stones from these areas that were given by the human players, and then to place them onto the foundation, either just placing them randomly or stacking them on top of each other to get a greater bonus. And then in the last 30 seconds, your goal was to pull out the foundation and then park where your robot was inside here, inside these triangles where the foundation is supposed to go into. So back to the control system. There are a few parts that you need to get your control system working. You'll need 2 Android devices. And first has a list online that you can find, and if you want afterwards I can point you to the list with all the legal devices you can use. And most of the time it's like a Moto phone or a Samsung phone. And you need 2 of them. So one of them would be something called the robot controller, which is this one, and the other one is called the driver station. So this is the robot controller. So it's basically the brains of the robot. It does all the thinking for the robot, and it tells it what to do. So it's an Android device, so in this case a phone, that runs this app called FTC Robot Controller. You can either download it as a file or get it off the Google Play Store. And so you have this as the brains, and then you have hardware options. So there's something called the Rev Robotics Expansion Hub, or the Rev Robotics Control Hub. And there are other alternatives, but these are the 2 most well known. So with the Expansion Hub, you have to connect the phone to it, and then the phone basically tells the motors to get, move or not move, or the servos to start or stop, or any of that types of stuff. And then this is the driver station. This is the second device, where the robot controller is on your robot, mounted safely and connected to the robot. Your driver station is with your drivers, and it basically connects to the robot controller using something called Wi-Fi Direct. And basically what that is your robot controller will create its own Wi-Fi network, and you just got to log on to that Wi-Fi network with, your phone right here. So with this, you can connect via the charging port to up to 2 controllers, And it also allows you to customize a lot of different things. So you can start and stop TeleOp and autonomous programs. You can check the battery that you're at. You can check the network and your ping to see if you're having a lot of latency with your robot. You can check your phone battery, set timer for 30 seconds or 2 minute 30 seconds for TeleOp and autonomous. You can also go into this area which is settings and customize, robot configuration, which we're going to talk about in a little bit. And the color of the app and all that different type of stuff. Set up network connections. So it allows the team to communicate wirelessly to the robot controller and issue commands to the robot controller. Just like the robot controller, it consists of an Android device running the FTC driver station app, also on the Google Play Store, or also, you can download it through the file. So what is the expansion hub? The expansion hub from Robotics is an I/O module. And what that means is it's an input-output. So we can receive outputs from it. So it's how the phone communicates with it. And it can also receive inputs, like motor inputs, of like all the voltage of the batteries and all those different types of things. And it allows the robot controller to talk to the robot. When an Android smartphone is used as the robot controller, you just got to connect them via a USB cable from the charging port into the back, which is going to be around back here. In the next slide, I'm going to show you what it kind of looks like. The expansion hub is connected to a battery, which powers the expansion hub and the robot. And the Android phone will use its own internal battery if it is used as the robot controller. And these two things work together to control your robot. So this is kind of a diagram that first made that shows off how this works. So we have our robot controller right here. It connects via USB to the back port right here. Then we have all these different sides with different things. So we're going to work our way around. This is where we can plug in our battery. So some people plug in the battery directly for testing, but when you're at a real competition, it's recommended to get a switch. And so basically it's an intermediate part right here. So you connect the switch into the hub and the battery into the switch. So you can just hit the switch and it turns the robot on or off into receiving power. Right here, you have 4 motor and 4 encoder ports, which you can use to plug into your DC motors. So this is the core hex, and this is just the normal DC, the HD hex, I think. Along the bottom, you can plug in 3-wire servos. You could also plug in VEX motors, the VEX 393 motors, if you're familiar with those, through the bottom. You can plug in analog sensors, as well as I2C sensors. So in this area, you can plug in, distance sensors, magnetic limit switches, touch sensors, color sensors, whatever you really want from here. So last year, Rev introduced a new expansion hub, basically called the Control Hub. And what it did is it allowed you to not even need to have one of your Android devices because it was built into the device. So for the Skystone season, teams in select regions had the option of using the Rev Robotics Control Hub. The Control Hub is an integrated version of the robot controller. It combines an Android device built into the same case as a Rev Robotics expansion hub. So luckily, my team was able to have this last season, and it's genuinely a lot better than having the expansion hub and the phone, because a lot of the times the USB connection is super finicky, and a lot of times last year ours just disconnected mid-match and we couldn't do anything about it. So having an all-in-one option is really great because you don't have to worry about having either of them, separately charged. You don't have to worry about charging the phone. The one battery will charge everything for us. So this is kind of the same deal of how it looks. We have our switch, our battery, motor encoders, 3-wire servos, our analog sensors, and our I2C sensors. Along the back here, which you can't see, there are a bunch of other ports. So they have an HDMI port, so you can look at visual. So what we did last year is we got a little Raspberry Pi screen. For those that don't know, it's a small computer screen, and you can plug them in through the back, so you can see a visual of what the robot was seeing. You can plug in a camera via USB. You can plug in a little SD card into it to save, logs and all that different types of things. Then there's a debugging cable, and then the cool thing is it runs with USB-C, which for those that don't know is the way that you're able to plug it in to the computer. And we're going to kind of talk about that once we get Android Studio set up. So if you want to learn more about how the control system works, you can go to this URL where we have highlighted how to get that set up. And since we're all at home due to quarantine, we didn't really need to add that to this presentation, but you can still add it, learn about it right here if you ever want to set up your phone and your robot control hub, all that stuff. So I'm going to go check the chat really quickly. Questions? Okay, cool. So this is something we're going to come back to in the next few weeks. It's something I like to call the development workflow, and we used it last year and it's really helpful. So it's a 5-step process that basically gets our entire autonomous pathway done, because TeleOp isn't as complicated for us. So what we do is we visualize and are planning out scoring. And you don't really have to understand why we do this right now, because we're going to kind of build upon it as we go on. So we first start out by visualizing and planning out our scoring. So in this instance, using vision to get the sky stones. We ask ourselves, okay, what do we want to do and how do we plan to do it? Then we test out the basic functions and operations. So, driving straight, making the perfect 90-degree turn, collecting the stone. We test all of them separately to make sure they all work on their own parts. Next, we have step 3, where we can test and refine our pathway. So what we do is we test out all these different parts, we start combining them and making sure they work in a basic pathway. And this is really helpful. So we make sure that there is no breaks in any of the portions, because a lot of times what people do is they'll make the code, they'll go straight to this step, and they'll never be able to test if it worked halfway through, and they'll have to restart all the way if it doesn't work from the beginning. So if we do this, then you avoid the amount of error that comes in when creating a pathway. So then we create our pathway. So drive straight, angle, grab the stone, turn, go down, out, take it onto the foundation. And then we do something called send to version control. And this is going to become really big next week when we talk about how to use GitHub and version control. So how that works is we just send a copy of all our code, and then GitHub will back it up. So if I never need to go back into using old code, we can just grab it, and then that easy. It basically allows us to minimize the amount of error. Any questions? No? Albino Crocodile 36, there will be a recording that we're going to be posting soon, shortly after this, if you ever want to come back, and we'll also post the slideshow. And we cannot do this on Roblox. I don't remember saying that as well. So, RZX 0201, unable to open. I think they fixed that issue, because what was happening is I think I ran into that issue multiple times at the beginning of the season as well, but as they came in with the new firmware updates, it got fixed. So maybe you should try again next season or get your hands on one to see if that's still an error. I know Rev was really helpful with it, because we ran into a lot of issues with our control hub last season, with it, randomly crashing in the middle of the field and us not being able to do anything. Like, the weird error was the Wi-Fi signal would still be on, but then the robot would also be on, but for some reason we kept on getting kicked off. For some weird reason, I have no clue why, but they gave us a new control hub, and that one works perfectly now. So the slideshow will be posted on STEMpump's website, and then I can send an email to you guys all after today. Yeah, so that'll be cool. Yeah. Okay, let's go to the next slide. So at the beginning, I briefly mentioned what an IDE was. So an IDE stands for an Integrated Development Environment. And so basically what that is, it's the place that we're going to program our code, where we type it out, all that stuff. In this camp, we'll be focusing on Android Studio. If if you weren't able to download it before or hadn't had the chance yet, please start downloading it now because it's the best time to do so while we're still talking, and then you can get that all installed. So for a lot of you guys that have been in part of FTC as well, you know what OnBot Java is. So Android Studio offers more freedom and flexibility when programming your robot. However, for most teams, the easier option is OnBot Java. For my first season, I used OnBot Java, and a little bit of last season I used OnBot Java, but around halfway through, I switched to Android Studio just due to the more flexibility we get with it. Because you can still, there is a way that you can get wireless uploading to your robot, even though it's not like out of the box. You can figure out how to do that, and we may talk about that next week if that's something you guys want to go into. But yeah, thoughts about IntelliJ. So IntelliJ is also a good option, and we're also actually going to be using that next week when I get the virtual robot set up. We're going to be using IntelliJ for that. You guys can still use Android Studio, but I'm going to use IntelliJ just to show you how the virtual robot works, and then I can also teach you guys how to use that. Post that link in the chat. Yes. So, yeah, we're gonna have a virtual robot hopefully next week where you guys can actually see the code that we're working on today, you know, actually work. So, you can learn more about how to set up OnBot Java at stempump.com/r/FTC, which links to our FTC curriculum. And like I said, since we're online, we don't really have most of the time or resources to really figure it out. And so, yeah, Android Studio is recommended for advanced users, but we kind of want to introduce it to you as an option to look at in the future. Even if you go back to using OnBot, it's still cool to kind of see how this works. So next, we're going to talk about SDKs, and that's a software development kit. First publishes a new one for every season, allowing teams to use new technology and control the robot. So right now, the current SDK is called Skystone. I'm pretty sure we're in version 5.4, something like that. And it allows us to, use the new, vision sampling that they give us. It allows us to use the new encoder stuff that they give us, new, weird sounds, and also being on the latest SDK version also helps you for the tournaments because they want you to be using one of the newer versions that will come out per season. So earlier in the week, I sent you guys an email. Hopefully you got it. And also when you sign up, you should have gotten a link to this. And if you go to this link, you're able to download the SDK if you don't already have it. Let me post this in the chat really quickly. And super random. You do not need to import settings because hopefully you've never used it before. If you have used it before, then probably import settings if it's something that you like to do. And you don't want to change any of your old stuff. Journeyman Joe said, if your school has hotspot blockers, oh yeah, that might cause a problem. But with Android Studio, you could potentially just do a wired connection and then upload from there, but it would be kind of hard to initialize any of that. So yeah, that might be some of the problems. I'm Turtle Best. IntelliJ, yeah, it is the same thing basically. It's just Google wanted to put a new name onto it, call it Android Studio. So now we're actually going to talk about OpMode design. So during an FTC match, the team's robot has to perform a variety of tasks to score points. Teams write OpModes, which stand for operational modes, to specify the behavior for the robot. OpModes are computer programs that are used to customize the behavior of a competition robot. The robot controller can execute a selected OpMode to perform certain tasks during a match. And earlier, I showed the driver station phone. That's the place where you can, execute your autonomous programs and your teleops, each which have their own OpModes. So there are two main types of OpModes. There's something called an iterative OpMode and a linear OpMode. So in an iterative OpMode, there's something called the loop method. And we're going to talk about that when we make our first teleop with an iterative OpMode. So the loop method is called repeatedly throughout the operation. So as long as your program is running, that loop will keep on going over and over and over until you end the program. The OpMode runs code through the loop and the other methods the entire time it's on. So I think there's around 5 different methods and it uses all of them. So the reason teams might be using an iterative OpMode is that it's super helpful for teleop because it just loops the same thing. Because during teleop, you don't want it to ever just do one thing at a time. You want it to, go through, so looping your controls over and over so you get precise feedback. And it's harder for autonomous. However, we will be talking about how to do an autonomous in this, not today, but later, using something called the state machine. And state machines can be done in a iterative OpMode in a really cool way. So the main reason a lot of people don't choose the iterative OpMode is it's difficult for beginners and there's not much need for it anymore. Because a little while back, first introduced something called the linear OpMode. And it's the new way to do everything now, basically. A lot of teams are using this. It's the easier way to do all of it. So it's the linear way to program, and it basically goes through the code one thing at a time. Once all the tasks are completed, the OpMode ends. And it's easier to understand and helpful for both autonomous and teleop. So in autonomous, you can say drive forward, drive backward, turn, and then it ends. However, if I said that in an iterative OpMode, it would drive forward, drive backward, turn, drive forward, drive backward, turn. Just keep repeating it over and over and over again. So what's next? We're going to be making the same teleop program using both types of OpMode design. This way, you can see what we like and want to use to program your robot. And then we're also going to be designing 2 different types of drivetrains today. We're going to be talking about the 2-wheel and the Mecanim drives. So for a 2-wheel robot, we have 2 wheels that are motor powered, and the other 2 wheels, most of the time it's 2, move in relation to this one. They're basically something we call quote-unquote dead wheels because they don't have any power being applied to them, no force. So the front 2 wheels and the back 2 wheels are providing all the power that controls the rest of the robot. So in another instance, you can use chain or tread to hook up 2 wheels to a single motor. So if you only want to use 2 motors on your drivetrain, you would connect it and then run the chain or thread or tread and then go through. Most of the time, those 2 motors are going to be connected to traction wheels, and those free spinning ones are omnidirectional wheels, because the omnidirectional wheel allows them to do that quick swivel that you can get from doing it. However, there are problems with this drivetrain, because it's a very basic drivetrain. Most teams go for an all-motor drivetrain where each wheel has its own motor. This gives more flexibility and freedom for the robot to perform more tasks. For Mecanim, one of the more recent and popular drivetrain designs, it is the Mecanim. So it allows for more horizontal, vertical, and diagonal movement, which makes it helpful for robots that need lots of freedom and flexibility. So if you can see here, we have these weird wheels that slant with little rollers on them. So what this allows us to do is we can drive forward, we can drive backward, we can also do something called strafe, so move horizontally while staying on the same axis or turning. So we're still going to be facing forward, but we can move left and right. And then we can also move diagonally, all while still facing the front. We can still turn, we can still, do whatever we want as a normal drive, but this allows a lot more flexibility in order to do what we want. But just like 2-wheel, there are some problems that come with it. Without advanced methods, it's harder to account for the slight drift and curve. Because what happens is since they're rollers, there's a lot of drifting that comes with them because of the loss of friction. So you're going to stop the robot and it might curve a little bit. Or while you're driving straight, it might curve a little bit to the left or a little bit to the right. But you can use the gyro to fix the issue up to a certain point. A lot of teams are doing something called odometry, which allows you to use something called a thorough bore encoder. And you have a small omni wheel on the back of your robot that's basically tracking all your motion so you can make sure that you can minimize the amount of drift and curve. So right before we get into programming and setting up Android Studio, I'm going to ask if there are any questions. Nope. All right. Okay. So when you get Android Studio installed, we're just going to set up a few things. So first, we're going to disable something called Instant Run. So we're going to go to Configuration, Preferences, Build, Execution, Deployment. Where is it? Instant. Unless they removed it recently. Where is it? Okay, so one of the questions was, what is a gyro? Yeah, and basically it allows you to change, figure out the directions that you are seeing. So if I have my robot, so this is at 0 degrees. Will be, if we turn this way, 90 or negative 90. We turn the other way, 90 or negative 90. So basically tracks the changing directions of your robot. So you can do 360. It's really helpful for turns, so you can make sure you get that perfect 90-degree turn. Someone asked if we're going to be going over odometry more. So basically, we won't go over odometry because it's very advanced, and the amount of hardware needed to actually test right now is very limited and scarce. However, we might be able to add it to our website later on in the summer, and we'd be able to share that information with you guys when that happens. When we'll be able to set up our own virtual robot? Yeah, so next week we're gonna kind of go through that, how we can. We'll explain how we got ours set up and how to set up yours. Oh my god! And then you guys can actually do this over the summer. If you don't have access to your robot, you can use the one that we provide from there. Okay. So open. So we're gonna click on Import Project. And then you're going to find your Skystone master folder and just hit open. And it will load this up. And you're going to see it's going to start doing something called indexing at the bottom. And let's update these really quickly. While we're doing that, we're going to go to Preferences. It lets me go to Preferences. Finish. There. Then we're going to go to Editor. And then we're going to go to General, Auto Import. We're going to click on Add Unambiguous. Alright, I pronounced that terribly. Imports on the fly, and this is going to make sure our coding is a lot easier. We're going to enable that, update that. So right here, it's going to take a little bit of time to just build through. So Android Studio says you have an SDK problem. So yeah, you don't have Java installed then. So if you want to get that installed, you can just Google, install Java and grab it from Oracle. You can just download it right here. And then you shouldn't have the SDK. Why does it look like your PyCharm? Because PyCharm is very similar. So you have the company called JetBrains, and they make a lot of great IDEs. I'm Turtle the Best was talking about IntelliJ, which is their Java IDE, and they made PyCharm, which is their Python IDE. And then Google came over and was like, hey guys, can we borrow your Java one, add Android, and slap it on the front to make it all cool? And yeah, that's basically what happened. So once we have that all set up, you should be able to say, it should say configure successful. You shouldn't have any of these things on the sides. So right now, the auto import setting. So let's just go back really quickly. You go to preferences. You can go click on editor, general, auto import, and just click on right here. Okay. So we have two main folders right here. So we have team code and FTC robot controller. So first, let's look at FTC robot controller. And so you don't need to matter about this, but we're going to open this Java file, and you see the word external.samples. This is all the code that, since the project file specified already exists. When you're in auto import, you want to click on the button right here that says add unambiguous imports on the fly. So right here under external samples, this is all the code that they give. So they have a basic OpMode with Iterative. I'm going to be making something almost very similar to this. They have a basic linear. They have examples of all the sounds you can do, servos, different types of drivetrains. So you have encoders, gyro, autonomouses, POV, and tank teleops. So you can just go through here. You can see all these different sensors. So we have color sensor right here, and it'll tell you how to use it. So it's really helpful because if you don't know how to use one of the sensors, you can just go here and it'll show it out. So if we open our team code folder, go to Java, and you can see we have this folder. So inside this folder is where we're going to be able to put all of our code, and it will show up. So let's get started on that. So if you right click on this folder, you can click new, and you'll see this thing called Java class. If you remember what I said when we were working on that hello world thing, I said that the class name is the same name as our file when we're first making it out. So what we're going to do is we're going to create our first TeleOp. So we're going to name our file that. So we're going to call it my first TeleOp L. And the reason we're going to label it with an L is because we're going to start off with doing a linear one. And then you don't have to change anything else. Hit OK. So right here we have this. This is our basic stuff. So first, let's tell the code that we want to use a TeleOp. So we're going to do @TeleOp, and you can see it's going to auto do everything. So if you see this, you can hit enter, and right here it automatically imports all the stuff we need for that. Then we add parentheses. We're going to type in name, hit enter, default, or name, default. And then here we can write the name that we want to show up on our robot controller and or driver station. So the file that we're going to click on. So we're just going to name it also my first TeleOp L. So then from here, we can actually, right before here, we're going to write extends linear OpMode. So what does this do? Basically what this says is it says, okay, we're making a TeleOp right here. We're going to call it this. This is my class, and it is a linear OpMode. So right here, right under here, we're going to start actually declaring our hardware. So we're going to be programming our two-wheel drive first. So we're going to create 3 DC motors. We're going to have a DC motor for our left drive, our right drive, and our arm motor. So this is another way we can actually declare variables. It's the same. So what this is we have int, right? We know we all have int number equals 5. So this is a variable type, and this is called an object type. So object is a very complex version of what a variable type is. So we're going to say right here, we're saying we're making a DC motor named left drive. And that's the exact same thing as saying we're making an int named number. We have not given it any value, so that's why I say it's a bit shaded like this. I'm trying to open. So it's the same thing as writing if we want, and so this right here is the same as writing DC motor left drive. That's gonna give an error. Right drive, DC motor, arm motor. This is the same thing as writing this. And we can only do that when they don't have values attached to them. So from here, we can create also a servo. So we can type in servo, type in enter, so it adds it right here. We're gonna call this clause servo. Add the semicolon to end it. Then we're gonna create something called an object. An object, like I said, is just like these, they're basically complex variable types built out of more variables, and they can keep track. So we're going to keep track of something called elapsed time, named runtime equals new elapsed time. That may seem super redundant because we said elapsed time runtime equals new elapsed time. That's how we say it. So then it initializes itself with preset values versus here where there's no values preset to them. Then we're going to declare a double. We're going to say double. Actually add variables. And also, if I hadn't mentioned, adding a double slash and then writing the word variables is how we create comments. So comments are completely ignored by the code. So that we can add text, we can write messages all right here. So we're going to write double servo position 0.45 semicolon. Then we can create an override. So we're just going to type in override, and then we'll write public void run OpMode. And you can see a bunch of our errors just one way. So this override basically says we already have a run OpMode from a linear OpMode, and we're just going to override that with our own code. So first we're going to do something called hardware mapping. And what that means is we're going to basically connect the code to our robot's hardware. So let's just do our first one. So we're going to write left drive. So this is our motor. Its name is left drive. Is equal to hardware map. We're going to write these parentheses. Our hardware map.get DC motor dot class, and give it the name that we're going to name it inside our robot configuration. So in your driver station or robot controller, you can click on settings and click configure, and that's where you're able to set names or give names to any motor or hardware that is on your robot. So it's different than the variable names because we're going to declare them in there. Someone asked, DC motor, why is it not this? Because these are uninitialized. We're giving this one, we're saying, okay, here you're an elapsed time, that's it. The reason is we initialize it here by telling it where it goes. When you run the OpMode, it connects to this. So you can actually do this exact same thing for a right drive. Get DC motor.class right drive. So in your configuration, you would write motor 0 is left underscore front. Or I should do left underscore drive. Then we could do that. And then let's create our arm motor equals hardware map.get DC motor.class arm underscore motor. We have this. Now let's actually do our servo. So it's actually the exact same thing, except we have to change what class we're using. So we'll do this class underscore servo. So I'm turn on the best. You can do it multiple ways. This is just a way that makes more sense when you read it. You can just say hardware map get the DC motor. Both ways work. It's just they have so many different ways to do hardware mapping that you can try anything and it still works. And yeah, get is a method of hardware map. You can use the other DC motor, because sometimes people will actually put that, and it still technically works. But I just don't use it that much. DC motor dot get. Yeah. I think they might have removed it, but I'm pretty sure I used to see it work. It does the exact same thing. It doesn't matter which way you do it. It just depends on what you're familiar with. So we have our class servo. Next, we're going to set directions. Directions. We're going to say left drive dot set direction DC motor dot direction dot forward. So when you put your motors on your robot, you orient them. You have your motor. Your left one, it'll go forward. It goes forward. However, if you don't see your direction, your right motor, when you tell it to apply positive power, will go the opposite way, because you reorient the motor. So do that, we're going to type in reverse. So then we know that our robot's going to be driving straight. Now we're going to talk about something called telemetry. And telemetry is basically data that we can return to the phone that you could use to get specific information back. So right here, okay, before we do that, what is hardware map? So hardware map basically allows us to map our variables to hardware. So basically saying, whenever I write left drive anywhere, I'm talking about the motor that is named left underscore drive. So from here, we can actually do forward reverse. So let's actually add our telemetry. So we can do, let's type in wait for start. So telemetry, we do telemetry.add line, and I'm going to write robot ready. Telemetry.wait, and then I'll explain what this is. So what happens is when you choose your, when you choose what program you want to run. So let's say we choose my first TeleOp. There's a play button. We hit the play button. As soon as you hit the play button, all this code in here runs, right? Up till this thing called wait for start. So that means all of this code up to here will run. So we want to know when our hardware mapping is finished, when the directions are set, and when we can hit the start or the play button or the start button. So then we can write robot ready. So when we know that that is the correct time to do it before anything is, set. So after wait for start is when any code would actually happen. So we see robot ready, we hit the play button, boom, robot starts actually doing something. So inside a linear OpMode, like I said, it does everything linearly. So basically, you're going to go one step at a time. But during a TeleOp, you don't need to do that. You need to be able to do everything for the entire match. So you're going to actually write something called while OpMode is active, and like this. So we didn't talk about what a while loop is. A while loop repeats something as long as what it's given is true. So we asked while OpMode is active. And this is a function or method that we're going to talk about later next week that either gives a true value or a false value. So when your OpMode is running, so after your wait for start, it's true, so this will run. But as soon as you click the stop button, this becomes false, and so does the rest of the program, so it stops running. So this loops through our code as we want. But right before here, what we're going to do is we're going to do runtime.reset. And what this does is it sets our variable, our object of elapsed time runtime, and it sets it back to 0. But why would we want this? And I'm going to explain this in a little bit why we want it. And it's to keep track of how many seconds have passed by during our match. So first, let's assign our gamepad. So if you have a normal gamepad with you, let me grab mine really quickly. Some of the basic inputs you have are A, B, X, Y. You have your triggers. You have shoulder buttons. You have maybe 1 or 2 joysticks. you have, and then you have a D-pad of sort. So inside here, we can actually give all these different inputs on our gamepad controller and apply them to how it looks as a variable. So first, let's create a variable called double, and we're going to call it drive equals negative gamepad1 dot, and here's all of our different variables. You have A, B, X, D-pad down, all these different ones. So we're going to actually choose Y. So why are we going to do this? So this is the left stick. So so first of all, we declare it as a double, right? Because how it uses a joystick is it's from 0 to 1 and 0 to -1. That's the application does. However, on a joystick, it's reversed. So when I move forward, it's -1. When I move backwards, it's 1, and when it's still, it's 0. That's why we negate it by writing negative gamepad. This gamepad 1, we can change it to gamepad 2, and you can use the second gamepad. The way to distinguish which gamepad is which is by connecting it to your phone and hitting Start A for gamepad 1 and Start B for gamepad 2. Then all the code that matches with Start that you did with your first gamepad, which is activated using Start A, will be with gamepad 1, otherwise gamepad 2. So we do our left stick and we do Y because we want to focus on the Y axis to move forward and backward. We don't want to worry about the X. Next, we're going to create another double, call it turn, and equal it to the negative gamepad 1. We're going to look at the right stick, the X. This is so we can do our turns. So like I said, all the inputs are negated for some weird reason, so we're going to negate it. So when I move right, the robot will turn right. When I move left, the robot will turn left. And it's on the X-axis. So we're not focusing vertical, we're only focusing on horizontal from left to right. The Y is from top to bottom or forward to backward. So now, let's create some more variables. We're going to write double left power and double right power. These are the individual powers that are applied to each side. So we can write left power equals, and we're going to do something called range clip. So range clip basically says, clip my number from A to B. So we go range.clip, and for range clip, we're going to do drive minus turn. So this is our variable. And then the value we want to clip between. So -1 and then 1.0. So what does this do? So we have our value, drive minus turn. So if you think about it, if I want to move forward, I'll move forward. So it'll be 1. It'll be a power of 1, right? I move forward, it's 1. So if I'm not turning, it'll be 1, right? Then if we do minus turn, so if I'm also doing it at the same time, if I'm driving forward and turning, it will subtract those values and apply that to the left side. So our left drive motor, it will be applying this value. We give it a minimum of 1.0 and a maximum of a minimum of -1.0 and a maximum of 1.0. This is the same as writing -100% to 100%. Everything is done in decimals. So if I wanted, so 80% is equal to 0.8. -60% is equal to -0.6. So you lock it between these variables because anything above 1.0 would still be considered 1.0, and it's just good practice to get into. So let's do our right power, however. Let's do range clip. So drive plus turn. We'll do -1.0 and 1.0. This is so we can get the turns and the forwards working perfectly, so you can use both controllers, both joysticks to perfect your driving. I'm losing it. Then let's create something for our arm. So we're going to do double arm power. And so right here, we're going to be using our triggers. So our triggers, when they're not selected, are 0. But when they're pressed all the way down, they are -1. And they're 1. So what we're going to do is we're going to negate it. So basically we're going to say, we're going to negate so when gamepad 1 dot left trigger is pressed, we're going to give it negative power. However, we're going to add gamepad 1 dot write trigger to it. So since both of them, when they're not being pressed, are zeros, if I only press down on write trigger, that is 1. So I'm going to apply positive power, right? Versus positive power. But what if I want to go backwards the other way? I do the left trigger, and it negates the same power. It will change it from 0 all the way to -1. So, but if I'm holding both of them at the same time, it will create a combination where I can either balance the arm or do something else like that. So from here, we can actually apply the power to our motors. So we can do left drive dot set power, left power, right drive dot set power, right power, and then we can do arm power dot set power, or not arm power, arm drive, or arm motor, arm power, and cool. So right from here, we can actually, now if we run our program, which you would plug in via USB, or if you get wireless set up, which we'll go over soon, or probably next week, you hit this play button and it'll run, and then you can test it out. But we're not done yet. Let's add some telemetry at the end, so we can actually keep track of how long the robot's been running. So we're going to do telemetry to add data. This is different than add line. We're going to write runtime, comma, runtime, dot, and we can choose the amount of time. So we're going to do seconds here, and then telemetry dot update. So up here, whenever you write telemetry in a linear op mode, you have to write telemetry to update, so you can send an update of the telemetry. Right here, we're going to write add data. So how this looks on the phone is it's just going to say robot ready. How this looks on the phone is it's going to say runtime, and then 30.243 seconds. Something like that, right? Something like that. So we have this. It adds a little colon, and it also allows us to make things a lot more precise. And then the telemetry update, we're going to update it because we want to keep on getting accurate time. And since we're inside our loop, it will keep on repeating over and over again. So that might seem like it's it, but we did forget something. We forgot to talk about our claw servo. So what we're going to do is we're going to add a conditional, and we talked about this a little bit earlier. So we're going to write if gamepad1 dot a is pressed. So gamepad 1, any button is considered a Boolean value. So it's true or false. If it's pressed, it's true. If it's not, it's false. Same with the shoulder buttons and the ABXY buttons. So if gamepad 1A is pressed, so if I press the A button on my first gamepad, I want to set servo, my claw servo, set position to servo position. And that should change it to 0.045. Now, if I hit B1, gamepad1.b, we get claw servo dot set position, and we can just go back by hitting negative servo position. We can change that to 0 if we want. So let's just do that. And then if we run it and we have everything hooked up, hit A and B, they'll switch their servos. So just like that, we created our first TeleOp. So what are we going to do now? We can actually, let's just remove that. So now we're actually going to focus on our iterative OpMode. We make the exact same TeleOp, but using a different type of OpMode. So we're going to do, you can do Control-N or just right-click, Java class, my first TeleOp. Oh, and this one might go a little bit faster because it's a lot of a repeat. So we're going to just do @TeleOp. Name my first TeleOp. Oh, extends. Now here's the thing. You would think we would write extends iterative OpMode, but actually we just have to write extends OpMode. So like always, we're going to declare our motors. DC motor, left drive, right drive, our motor. Servo, claw, servo. and then an elapsed time runtime equals new elapsed time. We're going to create our servo position. Okay, so how this works is we're going to do an override, remember, so we can override the original values. All right, public void init. And we're just going to write that, okay? Next, let's write at, or we don't need to, let's write public void init underscore loop, like that. Then after that, we're going to write override public void start at override public void loop. And remember, we talked about how this focuses on the loop, and we're going to do at override public void stop. And as you see, all of our errors went away because we declared all of these things. So now let's figure out where we have to place everything. So when we hit the init button on our driver station, so that's basically what's going to happen right here. So when we hit init, we're going to declare all of our hardware maps. Map.get DC motor.class left underscore drive. Right drive equals hardware map.get DC motor.class. Right underscore drive. Arm motor equals hardware map.get DC motor.class arm underscore motor. Claw servo equals hardware map.get DC motor.class claw servo, and I did catch that bug I made. Servo, there it is. Set our directions again. So dot set direction DC motor dot direction dot forward. Right drive dot set direction DC motor dot direction dot reverse. And that's it. So when we hit the init button, we want to make sure we declare all of these. Now what happens in the init loop? In the init loop, it's going to repeat over and over and over again throughout while we're in it. So before we even start the program, we hit the init button, then start, the program runs. So right here, let's just create some telemetry. So say robot. Ready? Right? So if you think about normal OpModes or iterative OpModes, is that we don't have to declare our telemetry.update. It automatically does it for us when we're declaring in a loop or anywhere around here. So that's one of the cooler parts about this one. So when we do start, what happens when we hit the start button? Well, all we actually need to do is reset our runtime, because there's no wait for start, because that's kind of built into here. So we hit start, that happens. This is basically controlling what happens. And then we lead directly into our loop. So right here, we're going to create the exact same thing. So drive equals negative gamepad1 dot left stick y double turn equals negative gamepad 1 dot right stick x double left power equals range dot clip drive minus turn negative 1.0 1.0, then the same thing, so double right power equals range dot clip drive plus turn minus 1.0 1.0 double arm power equals negative gamepad1 dot left trigger plus gamepad1 dot right trigger if gamepad1 And that's if we just write gamepad 1A. So this is the same as writing that. It's just a lot shorter way of doing it, and it's also a lot easier to read. You just say if gamepad A claw servo.set position to servo position if gamepad 2.b claw servo set position 0. So right after this, let's set all of our things together. So we're going to say our left drive set power to left power, right drive set power to right power, and we're going to set our arm motor set power to arm power. And then at the end, let's just declare our telemetry.add data runtime dot seconds. And that's basically it for our iterative op mode. So if we look at the differences between the two, can I do that? No, okay. So first of all, this one we have one of these things called run op mode. So when we hit init, everything up to here happens. However, when we hit init here, everything up to here happens. Same amount of things happening, but we have more we can distinguish more between the groups. We can loop, we can also do one. So a lot of teams, what they're going to do is they're going to use this iterative op mode for TeleOp and normally use a linear op mode for autonomous, because the linear op mode, they're able to designate each step that they want to happen, versus here, where you can use a state machine to do it, but a lot more work, versus the linear op mode where we can just get it done a lot quicker. So we have this. We don't need to set any of our updates. See, it all matches. Then we can, while op mode is active, very similar to our public void loop. And then all this is basically the exact same. You don't really have to add anything in the public stop, because once you hit stop, what do you really want to happen? I mean, you can upload logs or text files maybe if you wanted to your phone and maybe receive some data through there. But otherwise, there's not really anything you really need to use that for. So I'm going to check any questions. So is one stick pushed forward? Yeah. So it's backwards. So that's why we negate it right here. We change it backwards because for some reason, both of those values are reverse, which is the same reason why we negate the x. Double check something. Yeah. So let's we're gonna get a little bit into autonomous in the little amount of time we have left. We're on 7-10 minutes left. So we're going to explore more usages of the iterative op modes at a later time, so probably next week or the week after, where we talk about the state machine, because that's a really intensive Java program that we have to write with a lot of different pieces and parts to it, and we want to make sure that you understand all of the general stuff before we go that deep into it. So there's a lot of types of autonomous, or a lot of ways to program. Here are just a few of the types which we're going to go over. Many autonomous programs utilize multiple of these types. So all the bolded ones are ones that we're going to go over. We're going to go over time, which is what we're doing today. We're going to go over sensors and encoders and gyro, which is probably next week. And then vision, probably also next week. And if any of those don't fit, we'll move to the week afterwards. We're not going to go over odometry, like I said, just because due to the resources are low, and just a lot of people here that don't know a lot about the small things that we can't lead into the big parts of it. But we can talk about the whole idea behind it. So we're going to start off with time-based autonomous programs. These programs control motors by controlling the time per motor. However, time is connected to power. So if your motor will move faster for the same amount of time at a higher battery than a lower battery. So say your battery's at 14 to 15 volts, which is the recommended high that you can have. And it's working perfectly. Your autonomous is running every single time. Say you practice so much, it drops to 8. and your autonomous stops working. And then you go and change it. It's working again. It's just a little bit slower. You go tomorrow, you charge your battery, it's back at 14, 15, and everything is out of proportion. It's because, dude, there's so many variables contributing to the factor that in time-based autonomous, like the power is the main one, because power and time aren't really connected to each other equally. So we're going to create a program that drives a robot in a square. So this won't work perfectly on a robot because it depends on every robot's drive configuration with different variables in mind, such as wheel type, gearing, power, weight, influencing the program's function. Some double-check questions really quickly. And before we get to that, we might have to table this for another time so we can work on our autonomouses today. Our Mecanim drive today. So I think that's what we're going to end up doing today. So rather than making that autonomous that I just explained, we'll go over that next week. Let's make a really quick Mecanim drive. So we're just going to call it Mecanim drive. You could use either iterative or linear for this. It doesn't really matter, but we're going to kind of go through it. So set our name, Mecanim drive, extends, let's go linear OpMode, DC motor, left front, because we're going to attach variables to all of our motors. So 4 motors, left front, left back, and right back. Let's get our elapsed time. Then we're going to add our override, public void run OpMode. We're just going to hardware map really quickly. Just copy that. Okay, we have all these. Now we'll set our directions really quickly. Front dot set direction DC motor dot direction dot forward. So we're gonna set our left drive. So all the robot, so everything on the left side to forward, and the other ones to backwards, so reverse. Add our quick telemetry of an add line. Telemetry.update, and we're going to do our wait for start. Okay, we're going to do while OpMode is active. So here we're going to create 3 variables. We're going to create one for our forward. So as you guys know, the negative gamepad1 dot left stick Y. We're going to create one for our horizontal movement, otherwise known as a strafe. And that's going to be on the same joystick. That's going to be the x-axis. And then we're going to do one for our turn, which is equal to negative gamepad1 dot right stick X. Then we're going to apply all of this to our motors. And next week, we're actually going to talk about functions and methods and how we can condense all this code into way smaller portions so we don't have to write so much repetitiveness. So do set power. We're going to do range.clip. We all know this by now. So now we're going to do something cool. So it's going to be forward plus turn plus strafe, comma, negative 1.0, 1, and then 1.0. We're just going to do, so this is our first configuration. So when I drive forward on all of them, they add up together and create either a value between negative 1 and 1. And like I said, if we're only moving forward, that's the only value that counts because these two are both at 0. So it'll be 1 driving forward. I'm going to repeat these 4 times. We're going to do right front, left back, and a right back. So For our right, we're gonna do negative. This one we're gonna do negative here, and negative here. Now something you can do is we can create a double right here, and we can call it double clip. We can equal that to 0.8. So then rather than these, we can just write clip, place all those. And so why would we want to do this? So say your robot is super lightweight, and at 100% power, it runs way too quickly. And you want to cap the amount of power that's being distributed to each motor. Or maybe your drivers are saying the robot's too fast for them to handle. So with these clips, we can control it. So I say I only want them to run up to 50%. I write 0.5, and they can only drive up to 0.5. So even if they're holding the control all the way at max, it's only going to go up to 50% and only going to go back 50%. So that's really helpful when you want to be able to control the speed of your robot. Like last season, we used around 70%, because at 100%, the robot was way too fast for them to control when they're doing everything else at the same time. It also helps them doing precise movements. One thing that you could do is maybe have a conditional saying, when A is pressed, change my clip from 0.5 to 1. So say they need to they need to drive their robot really quickly into something to go park. Then it'll be at 1. Otherwise, when they're normally driving, 0.5 or 50%. Telemetry.runtime.seconds, and then telemetry.update. And that's all we need to do our Mecanim drive. So for today, anything that you didn't understand that you kind of want a brief reading about, you can go to this link right here, and you'll be able to read everything that we did today and a little bit more. Next week, we're going to start getting into autonomous programs, starting with our time-based ones and introducing sensors, encoders, and hopefully gyro and everything by then. These are all the camps that we have set up for the next few weeks, so you can sign up for all of them. So we have FTC Judging and Autodesk Inventor. Both of those are other robotics camps. So if you want to be able to CAD your robot, this is a really good camp to get into. If you're not doing so well in the judging process, this is another great camp to get into. Or if you just want to do any of these other things for fun, like we're going more into Java in a few weeks. We have artificial intelligence, RPG Maker, which is game development. This Thursday we have web design, and that's a really fun class to take. Python, and then Figma, which ties into web design. You can sign up for those at stempump.com/camps, or scan the QR code right here. You can download the app on the App Store, where you can also be able to access all of the online stuff. There's Twitch built in, so you can just watch through the app. You can register through the app. You can do everything through the app that you can do. Add us on social media. We'd love to hear from you guys on our Discord, Instagram, or even on Twitter, if that's something that everyone still does. And we'd love your feedback for today's camp. Today's was our first STEMpump Online camp, and I know it was a little bit rough, but I appreciate you guys for asking questions and telling me when I was going too fast or any of that. And you can also write some of the things that you are more interested in right here. Like if you want to learn a little bit more specific about the control system, or some of the programs that we did over the season, we can talk about those. But otherwise, thanks for joining the stream, and I hope to see you guys next week. So yeah.